Oil and gas has become a detrimental aspect to human existence, and removing these fluids responsibly requires extensive consideration. Reservoir engineering is the study of how hydrocarbons behave in rock formations at a subsurface level. Our team has leveraged various reservoir engineering principles to design and implement our selected development strategy. Our proposed design seeks to optimize the environmental impact and economic performance of the selected reservoir. Steelman Units 2 and 3 are located amongst the Weyburn Field in the southeast corner of Saskatchewan, Canada. This field is massive and spans across 3 states and 2 provinces with a total area of 210 square kilometers. From these various oil-rich pools, our team has concluded that the Midale Formation will provide the most opportunity for optimized oil recovery. The Midale Formation can be further separated into 2 types of rock laying on top of one another. The upper layer is distinguished as the Marley and consists of a more favorable dolomite matrix. The lower layer is referred to as the Vuggy, with a less desirable limestone matrix. Both layers of the formation have provided extensive hydrocarbon recovery, while more substantial investment has been placed on the Marley Formation. With an average porosity of 19%, the Marley is clearly much more capable than the Vuggy, containing a porosity of about 10%. Reservoir simulation is an incredible tool that allows engineers to create a virtual model of the reservoir. Various conditions can be imposed on the theoretical pool to simulate a parallel result in the true nature of the reservoir. Most implications to the reservoir come at high cost and are subjected to significant risk and uncertainty. By simulating these conditions, engineers and investors are able to feel more confident with these development strategies. The ultimate goal in reservoir simulation is to determine how well will the formation fluid move through the rock. In order to accurately simulate Steelman Units 2 and 3, the reservoir must first be constructed in this virtual space. This involves entering extensive amounts of data into the software and trying to recreate as much detail as possible. When general parameters begin to line up, the simulated model is ready to be run against historic data. History matching is the best tool for testing the accuracy of the model and enables the fine-tuning of specific parameters needed for simulation. Our team has studied a wide spread of particular aspects of this pool to determine the most feasible development strategy to propose. Converting the selected production wells into injection wells will address the issues in pressure loss and aerial sweep efficiency. This plan requires minimal capital cost and yields a considerable increase in production in the long run. There is also a relatively low risk associated to this strategy. Drilling horizontal wells in the northern region of the pool will enable additional recovery, especially in the more fractured regions. Drilling horizontal wells is considerably more expensive and comes with higher risk, making this development strategy a little bit less desirable. Replacing an outdated battery facility will lead to a significant increase in efficiency. As a result, this will lower the facility operating costs and reduce the environmental impact. This strategy requires significant capital investment and yields a modest long-term payout, making it slightly less favorable. Carbon dioxide injection is an additional avenue that must be considered, yielding massive payouts in nearby pools in the same Midale Formation. This development strategy has been known to increase recovery, typically providing a multi-million-dollar payout. Compounding this with proportional environmental improvements, it's highly encouraged to further investigate this option. Unfortunately, this strategy laid outside the scope of this project and was not fully pursued.